Dear students, in this module we will discuss the energy states of folded proteins. You would know by now that ab initio methods, they fold the proteins by looking at each atom individually and its bonding with each other. Now, if you have a bigger protein structure, a very large protein structure, then it is obvious that there will be numerous atoms that are surrounding the entire protein. Now, each amino acid and the protein backbone is comprising of these atoms. So, if the atoms are bonded together, if two atoms are bonded together, then some energy is released from the molecule. So you can say it has a net positive effect and the energy is reduced and therefore a negative value for such energy. While if two atoms are not bonded together and are imparting an electrostatic interaction on each other, then they are introducing instability into the protein structure. And therefore, the net effect is not good and the energy of the structure goes up and therefore a positive value for that energy. Okay, so here I have a cartoon of a protein which comprises of one alpha helix, some anti-parallel beta sheets, and a second helix. So in this case, let's consider these three amino acids, and as I just mentioned, each amino acid is composed of multiple atoms, and if there is a net positive and negative interaction between these atoms, then they are going to make a hydrogen bond. So as a result of the formation of such hydrogen bonds, energy is released. Energy is given out. So if your protein structure had this much energy initially, after the formation of this bond, hydrogen bond, the energy is lowered. So the energy given out is given by a negative number. Now, if we consider these two atoms from these two amino acids that are far away, then the chance of these two atoms making a hydrogen bond is very low, and therefore they will remain unbonded. Unbonded atoms, they typically contain energy and therefore destabilize the structure, and we'll consider both the bonded and non-bonded atoms during the ab initio modeling process. Okay, so let's start. As soon as you want to compute the overall energy of the structure, you have to compute the total non-bonded energy, the total bonding energy, and this will give you an overall evaluation or energy state within the predicted structure. In the simulation process, you create a force field. That is, you create an imaginary box like this, and this box contains your protein. And the protein is surrounded by H2O water molecules because they can perform electrostatic interactions with the protein, and therefore you can evaluate how stable or unstable your protein is, right? Okay, so let's take a look at how the simulation looks like. Here is your protein. It's an alpha helix, small protein, and here are the water molecules. This is O, this is H. So this side has a positive charge and this side has a negative charge, and the protein is going to interact with these water molecules. So once the protein interacts with these molecules, we'll see how many bonds are made, bond count, and then compute the energy. If you remember, the formula for computing the energy is non-bonded plus the bonded ones. Now, if you have computed the energy, now you want to change the protein structure in order to see the difference in energy given out by a different protein structure. So here it was an alpha helix, and now it has been replaced by 2 alpha helices and 2 beta sheets. So again, you compute how many bonds are made with the atoms in the protein, and therefore you compute the overall energy again. So in this way, you have your protein in a force field, and the environment is comprising of water, and all you're trying to count is the number of bonds that are made between the protein atoms and the water molecules. So once you have computed the energy of all possible protein structures that have been predicted, then you simply sort them by the energy content of each predicted structure, and the one with the lowest energy is the correct prediction. So this is the strategy that is used in ab initio methods. However, one very important question still remains, that how easy is it to compute the really lowest energy? So it means that you may think that a protein molecule is at the lowest energy state, but it may in fact be true that there is an even lower energy state that may be available, and you need to search for that even lower energy state during ab initio predictions.